Assalamu alaikum, students and physics enthusiasts. We analyze another problem on linear momentum conservation as applied to two uniform spheres in outer space. One sphere is twice as massive as the second sphere, but they both have identical radii. They are released from rest with their centers 40.0 meters apart. How do we find their speed when they are 20 meters apart? Find out by joining me till the end of this video. Watch and learn. The question is, an experiment is performed in deep space with two uniform spheres, one with mass 50.0 kilogram and the other with mass 100.0 kilogram. They have equal radii, r equals 0.20 meters. The spheres are released from rest with their centers 40.0 meters apart. They accelerate toward each other because of their mutual gravitational attraction. You can ignore all gravitational forces other than that between the two spheres. Question letter A. Explain why linear momentum is conserved. Question letter B. When their centers are 20.0 meters apart, find number one, the speed of each sphere, and number two, the magnitude of the relative velocity with which one sphere is approaching the other. And question letter C, how far from the initial position of the center of the 50.0 kilogram sphere do the surfaces of the two spheres collide? As illustrated in the figure, the center-to-center distance of the two spheres initially is 40.0 meters apart. They accelerate towards each other because of their mutual gravitational attraction. Their masses are given. M1 equals 50.0 kilogram, while the mass of sphere number 2, M2, is equal to 100.0 kilogram. And their radii are equal. So r sub 1 is equal to r sub 2, which is equal to 0.20 meters. The two spheres are initially at rest, and when released, they accelerate toward each other. And when their centers are 20.0 meters apart, we are required to find, all right, uh, the speed of sphere 1, denoted here by b prime 1, as well as the speed of sphere 2, denoted by b prime number 2. Also, uh, we are to determine the magnitude of the relative velocity with which one sphere is approaching the other, right? So we are talking about the absolute value of b prime 1 minus B prime 2. And in part C, our target variable, right, is D prime. This is the distance to the right of the center of sphere 1 from where it started until its surface touches the surface of sphere 2 just before the collision. For our solution, we are treating the two spheres as an isolated system, meaning we are assuming that there are no external forces acting on the system except for the gravitational force that each sphere is exerting on each other. Because the gravitational force is considered as an internal force within the defined system, right? So we use the energy method instead of Newton's three laws of motion. And the system starts with gravitational potential energy, right? Uh, but as the spheres move through each other, right, it will be transformed into kinetic energy as represented here by this equation. So negative delta PE is just equal to negative quantity PE prime minus PE naught, or that's equal to negative delta KE equals KE prime minus KE naught, right? Um, the final potential energy is denoted here by PE prime, all right? While the final kinetic energy is represented by KE prime. There is a negative sign in the term delta PE because the initial separation distance of the two spheres is greater than the final separation distance, right? So we express this change in gravitational potential energy and the change in the kinetic energy in terms of, all right, we have here um, negative delta PE is equal to negative quantity negative uh, capital G, all right? That's the universal gravitational constant multiplied by mass of sphere number 1 times mass of sphere number 2 divided by their um, this is their final separation distance, right? Minus quantity negative capital G M1 M2 divided by D naught, where D naught is the initial uh, separation distance, right? Which, when simplified, we can express negative delta PE as capital G M1 M2 multiplied by 1 over D minus 1 over D naught. And in the case of delta KE, or KE prime minus KE naught, that can be expressed as 1 half the mass of M1 times B prime 1 squared plus 1 half M2 B prime sub 2 squared, all right? The sum of these two terms represents the sum of the final kinetic energy of the two spheres, right? And then minus K naught is understood to be equal to 0 because initially they are at rest. So when you simplify this, okay, the delta KE is just expressed in terms of 1 half times m1 b prime 1 squared plus m2 b prime 2 squared. Consequently, we come up with this equation. m1 b prime 1 squared plus m2 b prime 2 squared equals 2 times capital G m1 m2 times quantity 1 over d minus 1 over d naught. Substituting the given quantities, all right, for the right side of this equation, we get, right, 2 times G m1 m2 quantity 1 over d minus 1 over d naught is equal to 2 times 6.67 times 10 to the negative 11. All right, we are doing away with the units uh, for the meantime. All right, so that will be multiplied also by 50.0 times 100.0, then multiplied by 1 over 20.0 minus 1 over 40.0. When simplified, we get, all right, 6.67 times 10 to the negative 7 times quantity 1 over 40.0. All right, so when you do our math, we get the value of uh, the right side of this, all right, working equation, which when equated to the left side of the equation, right, then we come up with our first equation, all right. Take note that in this equation now, there are two unknown variables, right? B prime 1 as well as B prime 2, or the final speeds of sphere 1 and sphere 2, right? So for now, we label it as equation number 1 because in a short while, we're going to derive another equation that will help us determine, all right, the two speeds B prime 1 and B prime number 2. As I said a while ago, um, there are two unknown variables, B prime 1 and B prime 2. So we need another independent equation, all right, which we are going to derive from considering that the total momentum of the system is equal to 0, all right? So P1 plus P2, all right, or M1 B prime 1 plus M2 B prime 2, okay, equals 0. So at this point, we have we can already answer question letter A. All right. Why is linear momentum conserved? All right. In this situation. All right. So the reason is that the system has no external forces acting on it. So the term is it is an isolated system, or we can also say that the summation of F, meaning uh, all the external forces, okay, that there may be, okay, is assumed to be equal to 0, right? So from this equation, m1 b1 or b prime 1 plus m2 b prime 2, we come up with the formula, all right, or equation for b prime 1. This is now in answer to question letter B, number 1. All right, b prime 1 equals negative m2 b prime 2 over m1 is our equation number 2. Right? And we are going to substitute this, all right, expression for b prime 1 here in this equation, which we earlier called equation number 1. So when we substitute b prime 1 into equation number 1, we get this equation now. m1 times quantity negative m to b prime 2 over m1, that will be squared, plus m2 b prime 2 squared equal to 1.67 times 10 to the negative 8. Actually, that is joules. This simplifies to b prime 2 squared multiplied by quantity m2 squared over m1 plus m2, and then equated to 1.67 times 10 to the negative 8. And substituting, all right, after we isolate b prime 2 squared, okay, 1.67 times 10 to the negative 8, okay, will be divided by m2 squared over m1 and then plus m2. m2 is equal to 100.0 kilogram. So when you square that and then we divide it by 50.0 kilogram, that's how we got 200. All right. And then plus the mass of sphere number 2 or 100.0 kilograms. So simplifying again, we get b prime 2 squared equal to 55.7 times 10 to the negative 12, right? And getting the square root of 55.7 times 10 to the negative 12, right? That becomes the value of b prime sub 2. With the help of your cycles, we get, okay, the speed b prime 2, or the final speed of sphere number 2, okay, equal to 7.46 raised to the negative 6 power meters per second. Going back to equation number 2, we cannot find b prime 1. That is, b prime 1 is equal to negative 100.0 kilogram times 7.46 raised to the negative 6 power meter per second, and then divided by 50.0 kilogram. When we do our math, we get the value of b prime 1 equals negative 1.49 raised to the negative 5 power meters per second. And since we're just after the, speed, all right, so the speed of or final speed of sphere number 1 equals 1.49 times 10 to the negative 5 meters per second. So, in part B, number 2, all right, where we find the magnitude of the relative velocity with which one sphere is approaching the other, all right, that is simply equal to the absolute value of b prime 1 minus b prime 2, or the absolute value of negative 14.9 times 10 to the negative 6 meters per second minus 7.46 times 10 to the negative 6 meters per second. So we get um, the magnitude of the relative velocity with which one sphere is approaching the other equal to 22.4 raised to the negative 6 power meters per second. The consequence of the conservation of momentum is, or conservation of momentum in a system is that the velocity of the center of mass will also be conserved. That is, the momentum of a system divided by its total mass will be the velocity of the center of mass. So we just need to find the center of mass at the starting point. And since the total momentum is equal to 0, the center of mass will not move. All right? So once the spheres collide with each other, the center of mass will just be in the same place. All right? So this is the general formula for determining the center of mass of a system, all right, which is equal to quantity m1 x1 plus m2 x2 divided by the total mass. So substituting our data into this general formula, all right? So we find the center of mass of the system equal to 50.0 kilogram, all right? That is the mass of sphere number 1 times 0, all right? Because we consider the position of the center of sphere number 1 to be our starting point. So x1 is equal to 0. And then plus 100.0 kilogram, that's the mass of sphere number 2, all right? And it is located 40.0 meters, all right, to the right of the center of mass or center of sphere number 1. And then that will be divided by the total mass of the two spheres, 150.0 kilogram. So doing our math, all right, we find the center of mass of the system equal to 26.7 meters. And in order for us to determine the location of uh, or the position of sphere number 1, the center of sphere number 1, okay, during the collision or just before the collision, we need to define a distance x prime 1, which is the distance to the right of sphere number 1 or the center of sphere number 1. That is where it started until collision, as well as the distance x prime 2, which is the distance to the left of sphere number 2. All right. Take note, sphere number 2 is moving to the left towards sphere number 1. So this is the center of sphere number 2 is where it started from until collision. We said that when the spheres collide with each other, the center of mass will be in the same place. So we once again apply the general formula for determining the center of mass. in order to find x prime 1 and x prime 2. That is 26.7 meters. This is the center of mass of the system at the start, all right, which you said remains the same, right, even during the collision. So when that is multiplied by the total mass, 150.0, right, their product will be equal to the mass of sphere number 150.0 kilogram, and that will be multiplied by x prime 1, right? And then plus mass of sphere number 2, 100.0 kilogram, multiplied also by x prime number 2. Simplifying, uh, by the way, we take note that x prime 2, all right, is actually equal to x prime 1 plus 0.40 meters, right? This is because um, x prime 2, which is a distance, okay, that will be covered by the center of sphere number 2, all right, at the start until it collides with sphere number 1. So 0.40 is just the sum of the two radii, right? And when we simplify this equation, right, we already consider by substituting x prime 2 by x prime 1 plus 0.40. So this becomes now 4005 equal to 50.0 times x prime 1 plus 100.0 times quantity x prime 1 plus 0.40. So doing our math, okay, we get 4005 equals 50.0 x prime 1 plus the product of 100.0 and x prime 1 plus the product of 100.0 and 0.40, which becomes 40.0. So simplifying further, we get 3,965. That's the result of transposing 40.0 to the left side of the equation. That means 4,005 minus 40.0 gives us 3,965, right? And adding these two terms, we get 150.0 x prime 1. So that x prime 1 will just be equal to 26.4 meters, right? So, in other words, upon collision, the center, all right, the center of sphere number 1 or x prime 1 is equal to 26.4 meters. Okay, so the distance x prime 1 equal to 26.4 meters simply means that the center of the 50.0 kilogram sphere is 26.4 meters to the right of where it started until the two spheres collide. All right? But our final answer in part C, okay, is not 26.4 meters. But in fact, it is the sum of 26.4 meters and the radius of sphere number 1. All right? The radius of sphere number 1, of course, is equal to 0.2 meters. So 26.4 meters plus 0.2 meters will give us 26.6 meters. And that is the variable that we are looking for in question letter C, denoted by d prime. So that is equal to 26.6 meters. Right? We interpret that to mean that the surfaces of the two spheres collide 26.6 meters from the center of the 50.0 kilogram sphere's initial position. Okay? So that's it. We're done. Till the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.